Yes, sir.
Okay, so we understood that the classical beamformer can be interpreted as a matched filter, which is optimal in white disturbance. The optimal clairvoyant beamformer can be interpreted as a whitening matched filter. And the whitening operation basically has the purpose to whiten the disturbance and so to revert the problem to the problem of designing the optimal beamformer in white disturbance. So the optimal beamformer is the cascade, can be interpreted as the cascade of two linear filters, the whitening filter and the matched filter. That's why it is called sometimes whitening matched filter. Clearly, most of the time, we don't know the structure of the normalized disturbance covariance matrix Q, so it cannot be implemented in practice. But its performance should be understood as a benchmark to the performance that can be asymptotically achieved by any adaptive detector. The power beam pattern of the optimal beamformer, as usual, is the modulo square of the filter impulse response H, calculated in the steering direction theta, that multiplies the array response A, calculated at the directional arrival of the source. So if you replace H with the expression of the optimal beamformer, remember K is irrelevant. You can get this expression for the power beam pattern. Then if you want that the maximum value of the power beam pattern is 1, we just have to impose the usual constraint, that the so-called distortionless constraint, H Hermitian times H equal to 1. So we impose this constraint and we find the value of K. The value of K that guarantees that this constraint is satisfied is 1 divided A Hermitian, the inverse of Q times A. So you replace K with this quantity, and so you find the expression of the optimal clairvoyant beamformer. Either you can express either as a function of the normalized disturbance covariance matrix or as a function of RW that includes also the power. I mean, they are perfectly equivalent. So if you find the power beam pattern with this value of K, this is the solution. And when theta equal theta t, this ratio is 1, and so you have the constraint satisfied. So in practice, the disturbance covariance matrix is unknown. So Q is unknown. And so also Ry is unknown. So in this scenario, where the disturbance covariance matrix is unknown, basically we have 3 different options. So the first option is very simple, obviously suboptimal, but from an engineering point of view is a very reasonable and realistic approach. Okay, we don't know Q. Okay, we implement the beamformer that does not require this a priori information. And clearly this beamformer is the classical beamformer. So we can implement the classical beamformer when the disturbance is not white, but its correlation structure is unknown. Clearly, as I said, this is a suboptimal approach, but very reasonable. And actually, this is what we do quite frequently. The second option that is frequently adopted in radar, especially airborne radar, is the following. If we have the possibility to collect a given number ns of secondary data vector that contains only disturbance, so do not contain the signal of interest. So for example, from adjacent REM cells, we can implement, so we can use the optimal beamformer, and we can obtain an adaptive version of the optimal beamformer, replacing RW with the sample covariance estimate. This adaptive version of the optimal beamformer sometimes is called sample matrix inversion beamformer, SMI beamformer. So the SMI beamformer is the adaptive version of the optimal beamformer, and it can be implemented only if we have enough secondary data vector that are not contaminated by the signal of interest. So that contains only disturbance. And so they can be used to estimate the correlation matrix of the disturbance. I mean, we say that this beamformer is adaptive because the impulse response H depends on the data, that you use to estimate RW. So the impulse response of the beamformer becomes data dependent and so adaptive. And I repeat, this adaptive version of the optimal beamformer is typically called sample matrix inversion because it contains the inverse of the sample covariance matrix estimate. And I repeat, what is fundamental is that we can observe NS realization of secondary data that have the same distribution as the disturbance. So they should not contain the signal of interest. They should not contain S of n. So if you have this data, we use them to estimate the disturbance covariance matrix. We calculate the inverse, we plug the inverse here, and we obtain our adaptive beamformer. Obviously, because the estimate is always affected by an error, there will be a loss in performance, in particular, a loss in terms of signal-to-noise ratio. So the signal-to-noise ratio that we achieve at the output of the beamformer is not the optimal one. So the one predicted by the formula that we derived before. But these three colleagues, Reed, Mallet, and Brennan, proved that if the number of secondary data vectors is greater than 2 times the number of sensors, the loss in performance does not exceed 3 dB. So the what is called adaptive loss, so the loss in signal-to-noise ratio due to adaptivity is lower than 3 dB. Sometimes it's possible to collect more secondary data vector than 2M, and a typical value that, I mean, we try to achieve whenever it is possible is an S on the order of 10 times M. So if NS is on the order of 10 times M, the loss is negligible. Otherwise, it depends on how many data we can process to estimate the covariance matrix. And this rule that says that if NS is greater than 2M, the loss is lower than 3 dB, is also called RMB rule. And it's very, I mean, it's actually an optimistic rule, but it's very frequently adopted in adaptive radar. The third option should be considered when we don't have data that are free of signal. So, but passive sensing, typically we can observe N snapshot, but this N snapshot contains both the signal and the disturbance. So the matrix that we can estimate is the data matrix Ry. So not Rw, but Ry. And if we replace in the optimal beamformer the estimate of Ry, we obtain another adaptive beamformer, and this beamformer is typically called Capon beamformer, or also minimum variance distortionless beamformer. So depending on which matrix we can estimate, the disturbance covariance matrix or the data covariance matrix, the whole data covariance matrix, we obtain two different adaptive beamformer. One is called this one, sample matrix inversion beamformer, and the other is typically called Capon beamformer. So you have to choose one or the other depending on whether you can collect secondary data contaminated by the signal or not. Actually, this beamformer can be derived also following a different approach. And I mean, the approach is very similar to the approach that we use to derive the classical beamformer. If you remember, to derive the classical beamformer, we try to minimize the power and the output of the beamformer subject to the distortionless array response constraint. To derive the classical beamformer, we made the assumption that Ry is equal to the identity matrix, and we solve the problem. If we don't make this assumption, so now we deviate from the procedure to derive the classical beamformer. So if we don't make this assumption, so if we leave Ry here and we solve this problem in the usual way by using the Lagrange method, so we want to minimize Q with this constraint, and the constraint is complex, so we need both this one and the complex conjugate. We calculate the gradient, we set the gradient equal to 0, we come up with the linear system of equation, we solve the linear system of equation, and we find the solution. The solution depends on the Lagrange multiplier. To find the Lagrange multiplier, we impose the constraint. So we replace this H here, and we find lambda in such a way the constraint is satisfied. And this is the value of lambda. And so you plug lambda here, lambda is real in this case, and this is the solution. And you find that this is exactly the optimal beamformer for the criterion to minimize the minimum to minimize the mean square error. Then we make it adaptive by replacing the unknown Ry with the sample covariance matrix. This beamformer, this adaptive beamformer, very frequently is called minimum variance distortionless response beamformer. So the MVDR and KPON are exactly the same. And this different name comes from the fact that we attempt to minimize the variance. So we attempt to minimize the power and the output of the beamformer subject to a distortion less constrained, that is this one. So that's why it is called sometimes the minimum variance distortionless response beamformer, MVDR. Clearly, when n goes to infinity, the sample matrix inversion beamformer and the KPON beamformer tends to the optimal clairvoyant beamformer, and so they tend to coincide. So they tend to provide exactly the same performance. But this is true only asymptotically. So for a finite number of available snapshot n, the performance are different. And we need to understand what are the differences, okay? So they coincide only asymptotically. We can use KPON also to estimate the spatial power spectral density, exactly in the same way as we use the classical beamformer. In fact, this is an estimate of the power. If you replace H with the expression of the KPON beamformer, you find that this is the power estimated by using KPON. If you divide by the bandwidth of the filter, which is on the order of the reciprocal of the length m, you find the spatial power spectral density, and depends on the angle because A depends on the angle. And you get an estimate of the spatial power spectral density, as we have done in the case of the classical beamformer, replacing the true Ry with the sample covariance matrix. So we plug R hat here, and we find an estimate of the power spectral density. And we can estimate the direction of arrival simply by looking for the peaks, the largest peaks, for the so we can estimate the direction arrival of the sources that are present in the environment by looking at the location of the K largest peak in the estimated spatial power spectral density. This beamformer is also adaptive because the impulse response of the KPON beamformer depends on the data through the sample covariance matrix. So that's why it is called adaptive. Okay. So if you remember, in summary, these are the two different expressions of the optimal clairvoyant beamformer, and they are equivalent, and they are obtained, one maximizing the signal-to-noise ratio, the other minimizing the mean square error. But if the noise covariance matrix is perfectly known, they are absolutely equivalent. And I mean, they are called, as I said, clairvoyant optimal beamformer. The Capon beamformer is the adapted version of this second expression of the clairvoyant beamformer. And obviously, when you replace the unknown Ry with the sample covariance estimate, because the estimate is affected by an error, there is a loss. And this loss is called adaptivity loss. So in other words, the signal-to-noise ratio that you achieve at the output of the Capon beamformer is smaller than the one of the optimal beamformer. I want to show some numerical result to compare Capon with the classical beamformer. And in order to show that Capon has better interference rejection capability. So it provides more accurate estimate of the directional arrival of the target. And the reason why it has better rejection capability comes from the inspection of the optimization problem that we solved to find Capon. To find the classical beamformer, we assume that the data are white, so we replace Ry with the identity matrix. If you don't remove Ry and you keep in the optimization problem Ry, it means that you try to minimize the contribution of the interference by using some information about how the interference is located in space, because this information is here. So in other words, because you keep in the optimization the presence of Ry, the result is that the beamformer that you find attenuates more where it is more useful. And this is something that the classical beamformer, which is non-adaptive, does not do. But I want to make this clear from some numerical examples. Okay. There is another fact that I want to show you, and it is the following. The classical beamformer does not use any information about the structure of the data covariance matrix. So you may have sources that are correlated, but because it does not make use of this information, is very robust to the presence of correlation between sources. Unfortunately, Capon beamformer, where in the expression of the beamformer you have the inverse of the data covariance matrix, if there are correlated sources, the covariance matrix tends to be either not full rank or ill-conditioned. So when you calculate the inverse, you may be in trouble. And you will see that I will show you through numerical examples, if some sources or some interferences are correlated, the Capon beamformer does not work well. So this is another case where it's better to use a suboptimal but more robust beamformer like the classical beamformer. So this is the case study. So this is the classical model of the data at the output of the array, so at the input of the beamformer. This is the structure of the data covariance matrix, signals plus noise. let's assume that the noise is white, the disturbance is white. Let's assume that there are k targets, k sources coming from these k different angles. The array is EULA. The signal samples are independent and identically distributed. So the various snapshots that we collect are mutually independent, but with the same distribution. So they are, we say, IID, independent and identically distributed. And the same for the noise. So if they are independent, it means that they are temporally wide. If the covariance matrix is proportional to the identity matrix, the noise sample are not only temporally wide, but we are assuming that they are also spatially wide. Okay. Instead, the signal sample are temporally wide, but spatially correlated. And the spatial correlation is described by this matrix here, ARS, Hermitian. And then we assume that both the signal and the noise are Gaussian distributed. The array is EULA. The distance between the elements of the array is the maximal possible, lambda over 2. The array is composed by 15 sensors. We collect 128 temporal snapshots. In the data, there are 3 sources. These are the 3 directional arrivals, -30, 0, and 60. And this is the correlation matrix of the 3 sources. Because this correlation matrix is diagonal, the 3 sources are uncorrelated. And because they are Gaussian, they are also independent. And the first 2 sources have power 1. The third source is weaker. It has power 1 over 4. And the power of the noise is 1. Okay. So if you derive the spatial power spectral density estimate by using Capon and the classical beamformer, this is what you get. Now, what can you get out of this picture? So you can see that the peaks of the Capon beamformer are much narrower than the peaks of the classical beamformer. This is because Capon make use in the design of the filter of an estimate of Ry. So in other words, it attenuates more those directions where the interference is present. And this allows Capon to achieve a better resolution. The fact that the resolution is better is suggested by the width of the peak. The narrower is the peak, and the better is the resolution. So Capon, for sure, has better resolution than the classical beamformer. And even the masking problem is reduced because you see that the side lobe are definitely much lower than in the classical beamformer. The price to be paid is the computational complexity, because you have to estimate the data covariance matrix, and then you have to calculate the inverse. So this increases the computational complexity. So the computational complexity to implement the classical beamforming is much smaller. You don't need to estimate anything. You don't need to calculate an inverse. And if the array is EULA, actually the classical beamformer can be very efficiently calculated by using the fast Fourier transform. So in favor of the classical beamformer, there is the computational complexity. In favor of the cable beamformer, the resolution, and in general, the estimation accuracy. So the choice is not so obvious. It depends if in your case, it's more important to keep low the computational complexity, or it's more important to achieve the best possible estimation accuracy. If the distance between, so in this figure, the directional arrival of the first source is -30, the second is 0. If the distance between the two is smaller, so for example, θ1 is -10, you can see that the classical beamformer tends to have problems because the two peaks are less and less separated. Instead, the two peaks of the cable beamformer are still very well defined. If the distance gets even smaller, so for example, 7 degrees, the classical beamformer is no more able to separate the sources. So the classical beamformer does not resolve the two sources, the two closed sources. And I mean, we assume that the power is the same. So from this point of view, it's an optimistic scenario. Things are even much worse if the power of the two sources is different, because in that case, in addition to have resolution problem, you can have also the masking problem. And I mean, you can see that the resolution of Capon is definitely much better than the classical beamformer. And this better resolution can be achieved only at the cost of an increase of the computational complexity. Clearly, if the power of the two sources is different, you can also have the masking effect. So for example, if the power of the first source, even if it is well spaced, is much lower than the power of the second, so 10 dB lower, you can see that the first peak is less pronounced. Okay, if they are well spaced, you can see the small peak. But if the distance is smaller, you may be in problem. And still, the cable beamformer has better ability to separate the two peaks, because this valley is deeper than this other. So from this point of view, cable beamformer has better performance, both from the point of view of resolution and from the point of view of the risk of masking of a weak source with respect to a strong, in the presence of a strong source. Clearly, at some point, if the sources are too close and the difference in power is significant, both method at some point doesn't work well anymore. This is clear, but I mean, Capon continue to perform reasonably well, even in scenarios where the classical beamformer does not work anymore properly. So we can make a number of remarks about our adaptive beamformer. So here it is reported remarks for the sample matrix inversion beamformer, but I mean, what is reported here is is true also for the Capon beamformer. So when the number of temporal snapshots is large enough, the performance of the sample matrix inversion beamformer and of Capon beamformer tends to the performance of the clairvoyant optimal beamformer. So if n is large enough, the adaptivity loss is negligible, and so Capon and sample matrix inversion beamformers tends to have the same performance. If the disturbance is dominated by jammer, which is directional, the RMB rule should be replaced by another rule that says that basically the number of snapshots should be at least twice the number of jammers. So not twice the number of sensors, but twice the number of jammers. In order to have only a 3 dB loss with respect to the optimal. This is true only if the disturbance is dominated by jammer. So the jammer to noise ratio is very large. Then another comment is the following. The classical beamformer does not require to calculate an inverse. The adaptive beamformer, both the sample matrix inversion beamformer and Capon, both of them require to calculate the inverse of the sample covariance matrix. So if the number of snapshots that we use to estimate the matrix is smaller than the number of sensors, so is smaller than the size of the matrix, the sample covariance matrix is singular. So the rank is equal to n, which is smaller than m. So it cannot be inverted. And so we are in trouble. So if n is smaller than m, we cannot implement the adaptive beamformer because we cannot invert the sample covariance matrix. But this is not the only case where we are in trouble, because even if n is greater than m, so theoretically you can calculate the inverse. But because of the error in the estimation, the matrix is ill-conditioned. So if n is small, it may happen that the matrix is ill-conditioned. When you calculate the inverse, the result is basically totally wrong. So you cannot rely on the inverse, because if the matrix is ill-conditioned, all the methods to calculate the inverse doesn't work well. So if we are in the small sample size case, we are in trouble. In that case, one option is to use the classical beamformer, which does not require any calculation of the inverse of a matrix. So we can say that the performance of the sample matrix inversion beamformer are very sensitive, so strongly depends on both the small sample size, but not only, they are affected also by a mismatch between the true direction of arrival of the signal and the steered direction. And I mean, we can have this kind of problem. Why? Because you cannot steer the beam to any continuous value, let's say from minus 90 degrees to 90 degrees. We point into an angle, and then we switch to another angle, and then we switch to another angle. So we point the beam on a grid of points, and not necessarily the true signal comes from a direction that is on the grid. So we can have an off-grid problem. So we never point the beam exactly in the direction of the source. So this is called off-grid problem. And it's a problem of many directional arrival estimation methods. And so there is a mismatch between the steered direction and the true directional arrival of the signal. And even this can create a loss in performance. So in general, there are a number of causes for signal mismatch. So there can be a pointing error that I just mentioned. The source can be not point-like, so could be a spread source. And this also creates a mismatch between the assumed array response and the true one. There could be multipath. Multipath can create some correlation between different sources. There can be any non-ideality in the design of the antenna shape. The array can be poorly calibrated, so we don't know exactly where the sensors are, and we don't know exactly the frequency response of each sensor. There can be some distortion for the wavefront during the propagation because the medium is not perfectly non-dispersive. Sometimes the medium is homogeneous, and this creates wavefront distortion. So the wavefront is no more perfectly planar, and so on. I mean, there can be other reasons. What are the effects of this kind of non-ideality? The effects are mainly two. The first effect can be termed signal self-nulling, and in particular, in the presence of an error, a mismatch in the signal steering vector, so a mismatch in the pointing direction, the adaptive beamformer, so both the sample matrix inversion beamformer and capon, tend to interpret the signal as interference because it comes from a direction that is slightly different from the pointing direction. And so they try to suppress. And if they never steer the beam in the true direction, it may happen that adaptive method cancel the signal of interest. You don't see it. So this is called self-nulling. And it's a problem, obviously. And this may happen also due to the fact that we have a small number of snapshots to estimate the covariance matrix. And the other effect of these sources of non-ideality can be the increase of the side lobes. So in the beam pattern of the adaptive beamformer, because of this non-ideality, you can have very large side lobes. And this happens especially in a scenario where the sample size is small. So when the number of snapshots is small. And with all the problems that you can imagine, because if you have large side lobes, you can have demasking. Now, before showing some numerical example and before telling you how to cure this problem, let me remind that the Reed, Mallet, and Brennan rule basically can be applied only when we have secondary data vectors that are not affected by the signal. So if we can observe a number of realizations where only the disturbance is present, and we can estimate the covariance matrix of the disturbance. If this is not possible, and we can only observe n snapshot where not only the disturbance, but also the signal is present, in that case, the rule should be replaced by another rule. And this other rule says that n should be greater than the optimal signal to interference plus noise ratio multiplied by n minus 1. And if the signal to noise ratio is large enough, so SINR greater than m, it means that n should be greater than m squared, which is much larger than 2m. So in other words, if your snapshots are contaminated by signal, the convergence to the optimal performance of the clairvoyant detector, of the clairvoyant beamformer, are much, much slower. So the convergence rate to the performance of the clairvoyant beamformer are much lower in the case where we cannot collect signal-free secondary data with respect to the case where we can collect signal-free secondary data. So the presence of the signal in the data make the convergence much slower. And so in this case, we need to introduce some robustness in our adaptive algorithm. Let me show another numerical example, and then I will pass you the MATLAB code, and so you can rederive these results, okay? Okay, so I want to show you through some numerical examples what I just stated. So let's assume that we observe n independent and identically distributed snapshot. Each snapshot is made by signal plus interference, directional interference, plus white noise. So we have the point-like signal, the point-like interference coming from another angle, plus white noise. The array is EULA. So this is the array response. The signal generated by the source is a Gaussian process, complex Gaussian because it's the complex envelope, with zero mean and some power. The jammer is also a Gaussian process with zero mean and its power. And the noise is temporally and spatially white, and it's a Gaussian process. So each snapshot is a Gaussian process, is a Gaussian vector with zero mean vector and covariance matrix Ry, that is the sum of the signal plus disturbance. And the covariance matrix of the disturbance is the covariance matrix of the jammer plus white noise. So you can express in this way, where sigma W squared is the total disturbance power, jammer power plus noise power. This is the array gain of the optimal beamformer, you remember it is A Hermitian Q to minus 1A. This is the sample matrix inversion beamformer, where we can estimate the disturbance covariance matrix by using secondary data that are not contaminated by signal. If instead we have data contaminated by signal, so if you can only observe signal plus noise, the adaptive version of the beamformer is the Capon beamformer. So in other words, Capon is equivalent to the sample matrix inversion when the signal is present in the data. So that's why I use the same subscript here. But there are two scenarios. The case where we can estimate the disturbance covariance matrix, and the case where we can estimate only the signal plus disturbance covariance matrix. Now, if you plot the output signal to noise ratio, which is given by this expression here, so you can calculate the signal to noise ratio of the output for this and this by plugging here H. So you have to replace H with this or this. So if you plot the signal to noise ratio of the clairvoyant, it is a constant. It does not depend on the number of snapshots, obviously. And it is given by this. And if you calculate with this number, it is 30 dB. And then you plot the output signal to noise ratio for the adaptive beamformer that can estimate the disturbance covariance matrix, so that can observe signal-free secondary data, and you compare with Capon, so the sample matrix inversion that has to estimate the total data covariance matrix, so signal present, you can see that the convergence to the optimal signal to noise ratio in the second case, so if we have data contaminated by signal, is much, much slower. In this case, this is 20, no, this is 20, 30. Here, after 30 snapshot, you can achieve almost optimal performance. Here, you need many, many more. So this is 3M. Here, remember, you have M squared. Even more. Now, let me describe what happens if there is an error in the pointing direction. So if the signal is coming from direction arrival theta t, so if there is no error, so if you point the beam pattern, if you point the beam exactly in the direction of the source, you are implementing this adaptive detector. If there is an error in the pointing direction, you are pointing to a direction that is the true value, the true direction arrival of the source signal, plus an error delta theta. Now, let's assume that we have data contaminated by signal in both cases, and let's compare what we get in two different cases. So no look direction error, first case, look direction error, second case. If you compare the two, assuming, for example, that the error in the pointing is 1 degree, you can see that in the absence of look direction error, Capon tends asymptotically to the performance of the clairvoyant. If there is an error in the pointing direction, you never reaches the optimal performance. So you have a loss, and this loss does not tend to zero when n increases to infinity. So you can understand that we should introduce some robustness in our adaptive beamformer exactly because we expect a look direction error to be always present because you steer the beam in a number of finite directions. So you select some angles on a grid, but there is no guarantee that the true directional arrival is on this grid. And so the possibility of a look direction error is always there. It's pretty realistic. And the solution is, there are many solutions to this, but the most widely adopted solution that is implemented in almost all radar, at least in those more expensive, is a regularization technique that is generally called, at least in radar, diagonal loading. And it's very simple. So when you estimate the covariance matrix, so when you implement the sample covariance matrix, after the estimate, you add this term delta, which is the loading factor, on the main diagonal. That's why the technique is called diagonal loading, because you add something deterministic that does not depend on the data on the main diagonal. So it is called diagonal loading. The effect is that basically you reduce the air conditioning of the matrix, because a measure of air conditioning is what is called Rayleigh quotient. And the Rayleigh quotient is the ratio between the highest eigenvalue to the lowest eigenvalue. The larger is this ratio, and the worse it is. If you do this loading, basically you reduce this ratio. So you reduce the air conditioning, so you make the inverse more stable. Now, to understand the effect of this loading, you can think what happens in the two extreme situation. If delta tends to 0, you tend to Capon. So you go back to Capon. If delta tends to be very large, it means that this second matrix dominates on the first one. So it is like if you assume that the data covariance matrix is the identity matrix. So when lambda delta increases, it tends to the classical beamformer that assume this matrix to be the identity matrix. So basically, when delta tends to 0, you tend to Capon. When delta tends to infinity, you tend to the classical beamformer. Controlling delta, basically you have a compromise between the two. So you get a good compromise between the better performance of Capon, but more robustness of the classical beamformer. So controlling delta, you control the trade-off between accuracy and robustness. So if you increase delta, you increase robustness, but you worsen the accuracy, and vice versa. Now there is no optimal rule to select delta. So delta should be selected based on the experience, actually. So the good designer should have enough experience to understand for his application what is the best choice for delta. But there is no equation that can be solved that tells you what should be the value of delta. And the nice thing is that by introducing this diagonal loading, it has been proved empirically, so experimentally, that the beamformer becomes more robust to any kind of non-ideality. And I will show this through some numerical examples. So the idea is the following. We calculate the sample covariance matrix. We adopt the diagonal loading, and we implement either the sample matrix inversion or the K-con beamformer with diagonal loading. So for example, if you apply diagonal loading to the SMI beamformer, what you get is the so-called loaded sample matrix inversion beamformer. So it is denoted by the acronym LSMI beamformer. So the letter L refers to the fact that we are resorting to the diagonal loading technique. Now, what happens if we use diagonal loading? You can see that, for example, in the presence of a loop direction error, without diagonal loading, you achieve asymptotically some performance. If we introduce diagonal loading, okay, you don't achieve the optimal performance, but you can make the beamformer much more robust to a loop direction error. So you can achieve much better signal-to-noise ratio at the output of the beamformer. This is with a choice of delta equal 20 times the noise power. And this is another scenario. So where the geometry-noise ratio is different. So depending on the value of all the parameters, you can get more or less closer to the optimal one. But what is important to understand is that by using the diagonal loading, you make the adaptive beamformer much more robust to sources of non-ideality. And these sources of non-ideality includes a loop direction error, but also small sample size. What about the beam pattern? And this is the beam pattern in the presence of the same pointing direction error. And you can see that in the presence of pointing direction error, without loading, one effect is that the side lobe becomes very large. With the loading, you can also stabilize much better the side lobes. So this is one example. This is another example. And I repeat, there is no theoretical proof of the benefit of diagonal loading. The benefit of diagonal loading have been verified experimentally or by Monte Carlo simulation, like in this case. So the loading is very helpful also to stabilize the side lobe of the beam pattern. This is another example. So, closing remark on this part. So diagonal loading is a very simple, widely adopted in real radar method for side lobe control. There are other methods, but are much more sophisticated. So diagonal loading is very simple and very robust. There are other methods that, for example, this Turner beamformer is very useful, but only in scenarios where the signal is weak and the noise is dominated by directional interference. But I don't have time to enter in the details. So, in 20 hours, we have time only to summarize the most fundamental facts in array processing. This is another example, numerical example. And then I'll show you this example, and then I will pass you the MATLAB code. And so you can run the code and rederive the same results, or you can change the parameter and see what happens. In this example, I want to compare capon without diagonal loading with capon with diagonal loading. So the assumption about the data model are exactly the same, so I'm not going to repeat, are exactly the same as before. We assume that there are three sources coming from this angle. The covariance matrix of the signal is the same as before, so the three sources are uncorrelated with power 1, 1, and 1/4. The noise power is 1, and I'm assuming to set the loading factor equal to 5 times the noise power. So this is what you get. So there are three sources, so you see three peaks. This capon beamformer. This is the green one is the classical beamformer that cannot separate the first two sources. So classical beamformer has not enough resolution to separate the first two sources. If you use diagonal loading, in this case, where there is no pointing direction error and the sample size is reasonably large enough, it works well, but obviously not as well as capon. So it's obvious that when you introduce the loading, you sacrifice estimation accuracy, but because you want to introduce more robustness. Now, if all the model is ideal, the performance gets slightly worse than capon. But if, for example, two sources are correlated, for example, the second source and the third source are strongly correlated, so the correlation coefficient is 0.99. Well, in this case, you can see Okay, I think there is a mistake in the view graph. Let me check and correct. Just 1 second. Okay, I made a copy and paste, and I forgot to remove this. Basically, I will send you the corrected view graph, okay? So if all the sources are uncorrelated, Capon correctly separate the 3 sources. If the source 2 and 3 are strongly correlated, with the same power, even with the same power, this is what happens. What happens is that Capon does not show any more 3 peaks, but the number of peaks is basically equal to the rank of the matrix, and the rank of the matrix is in practice 2, because 2 sources are strongly correlated. Capon, which does not require the inverse, the classical beamformer that does not require the inverse of the matrix, still is able to see 3 different peaks. Diagonal loading with this loading factor, which is a trade-off between the two, does not work well. But if you increase the loading, things works a bit better. If you increase further, I think we should be able to see 3 peaks. So in this scenario, where the sources are strongly correlated, diagonal loading Capon performs a bit better of Capon. So I will send you now all the MATLAB code, so you can spend the last 10 minutes to rederive some of these figures, and obviously you can use them tomorrow morning. So here it is. So I just sent the MATLAB code for adaptive beamforming. So let me know if you receive it and you can circulate. Did you receive the files?
Yes, sir, we have received we are sending it to other participants.
Yes, we are sending. Yes.
Yes, we received it, sir. We received it.
Okay, so I mean the last figure that I show have been obtained by using the file called classical versus capon and diagonal loading capon. The other have been obtained by running the file classical versus capon beamforming. And the plots of the signal to noise ratio versus the number of snapshot is the last this one. And so I mean by the name, if you run, you can understand immediately. So you can rederive all the figures in this chapter. We have not finished the chapter, but we continue tomorrow with the theory. But in these last 10 minutes, I think you can take one of these program and run and to see what you get, and you can change some parameters. So for example, I want to increase the delta. Instead of 10, like in the last figure, I put 20 times the power. Yeah. Improves, but not much. So I made a correction to chapter 4 and I send again the PDF.
Okay,
So
sir.
you can distribute.
Okay, sir.
So again, the code is pretty simple. And I don't know if you can read in the screen. But I put also comments, so I think you can understand the structure quite easily. And as usual, at the beginning, I set all the values of the parameters, and then I comment more or less each step. So it should be very easy to follow. So I implement classical beamformer, and then capon, and then diagonally loaded capon, and then we compare. In a figure, we compare the estimated power spectral density by using the three different methods. Okay, I think we can stop here, and tomorrow we continue to talk about beamforming, and I think because I have to cut something.
Yeah, sure. If you have any doubt from anyone, please ask. Otherwise, we can close the session for today.
Yeah, let me. So just 1 second. I sent you the next chapter for tomorrow.
Sure.
Okay. So the next topic is model-based beamforming, so parametric beamforming. So we have seen the classical beamformer, which is non-parametric, so non-model-based, non-adaptive. Then we have seen sample matrix inversion, capon, diagonally loaded capon, diagonally loaded sample matrix inversion. They are non-parametric, so non-model based, but they are adaptive. And the third big category of beamforming method are the parametric method or model-based method, and we will talk about them tomorrow.
Okay, thank you, sir.
So just 1 second, I create the PDF and I send it to you. Okay, here it is. Okay, see you tomorrow.
Okay, sir. Thank you.
Thank you.
Bye.
Thank you. Thank you, Professor Gill.
Bye.
Bye. Bye.